By 2050, the population of Earth will be about 10 billion people. This will inevitably lead to an at least twofold increase in our need for energy. Nevertheless, by the end of the century, there will be too little coal, oil and gas left on our planet to provide the humanity with warmth and light. Unfortunately, this scenario, which may seem fantastic at first glance, may very well become a reality. Scientists are sure there is only one way to avoid a global energy crisis of the future: to create an alternative and inexhaustible source of energy. For example, learn to control the thermonuclear reaction. The very reaction that is constantly occurring on the Sun, making it generate an enormous amount of energy. But why did we actually decide that we're capable of lighting up our own Sun on Earth? How? In what conditions are scientists taming thermonuclear fusion today? Finally, will we be able to create the inexhaustible source of energy that we're dreaming of by the end of the century? The Sun is the central and the only star of our solar system. Also, the Sun is actually a thermonuclear reactor which has been running for almost 5 billion years already. Every second, the star pours the surface of the Earth with the energy the production of which would require dozens of millions of power stations. But how is our star capable of producing such a colossal amount of energy? The solar core is heated to 27 million degrees Fahrenheit. A temperature this high is one of the most important conditions for a thermonuclear reaction. Its main component is hydrogen. In the bowels of the star, this chemical element is ionized and thus represented in the form of protons, nuclei of hydrogen atoms. At such a huge temperature, protons fly so quickly that they approach each other and collide. This is how the proton-proton cycle is launched, when a light element, which is hydrogen, turns into a heavier one, helium-4. This exact difference in masses obtained during fusion is converted into energy, according to Einstein's famous formula. Energy equals mass times the speed of light squared. Overcoming the distance of almost 93 million miles to Earth, the power of solar radiation inevitably weakens. On the orbit of our planet, it roughly equals 1,370 watts per square yard. An even smaller part of each, about 1,000 watts, reaches the surface, but only during the day, in clear weather, and in the equatorial belt. The rest is lost in the dense layers of the atmosphere. But even this is more than enough for sustaining the life on Earth for billions of years already. After realizing in the first half of the 20th century what exact processes in the Sun generate power, scientists thought, what if we reproduce the energy of the luminary in the terrestrial conditions and seize the energy of thermonuclear synthesis? So how did the scientists manage to replicate on Earth the processes that take place in the Sun, a huge glowing gas ball that exceeds the mass of our planet 333,000 times? It turned out that to light up a star, it is only necessary to borrow the principle of the thermonuclear reaction of the Sun. Slightly different operating elements were selected to achieve fusion in the terrestrial conditions.
On Earth, we have much more efficient fuel than the one available for the stars. We can even say that this is our advantage, the advantage of humanity before nature. Nature basically only has regular protons to start a nuclear reaction. We can make the fuel much more effective if we use deuterium and tritium.
Deuterium and tritium are isotopes of the lightest chemical element, hydrogen. Deuterium is a heavy, stable isotope, the nucleus of which consists of a proton and a neutron with a total mass of 2 atomic units. Tritium is a super heavy and radioactive isotope of hydrogen. Its nucleus consists of a proton and 2 neutrons with a total mass of 3 atomic units. As early as in the 1950s, scientists came to the conclusion that with these heavy isotopes of hydrogen, it is possible to perform a thermonuclear reaction. Deuterium and tritium can also be found in nature. Moreover, there are literally oceans of deuterium on our planet. This hydrogen isotope is found in seawater. The situation with tritium is a bit more complex. It is formed in small amounts in the upper layers of the atmosphere, upon collision of space particles with nitrogen atoms, for example.
Unfortunately, it is a rare material, and it has to be specifically created. Currently, it is mostly received as a byproduct of operation of heavy water reactors. On the other hand, it can be specifically and artificially created. There are certain process schemes for a thermonuclear reactor, where lithium is converted to tritium during neutron irradiation due to the course of reaction. This tritium is collected and provided as fuel for thermonuclear reactors.
For a successful thermonuclear reaction, the mixture of deuterium and tritium must be heated to ultra-high temperatures, 90 and even 180 million degrees Fahrenheit. This is several times more than the temperature of the solar core. This is the only way the nuclei of deuterium and tritium can accelerate and overcome Coulomb repulsion forces in the gas mixture of hydrogen isotopes, which is transformed into fully ionized plasma. This will allow the atoms to merge, forming a neutron and a helium core. As a result, the energy, equal to 17.6 mega-electron volts, will be emitted. However, before implementing this scenario, scientists had to solve a serious problem: figure out where and how to keep the incredibly hot plasma in order to prevent the thermonuclear reaction, both from going out and from destroying the reactor. In the Sun, the incredible gravity takes care of this problem, but it's impossible to recreate it on Earth. It would seem an insoluble task, but a way was found.
Plasma is an electrically conductive liquid, or a gas to be more precise. It behaves both like a liquid and like a gas. Therefore, it is natural to try and lock it inside a certain volume. But it is impossible to lock it that way. Plasma won't understand it. It will spread across the walls of the volume and go out. And that will be it. Accordingly, there should be a vessel of some kind that will hold the plasma. Magnetic field can be used as such a vessel, since the plasma obeys the laws of magnetic hydrodynamics and doesn't go beyond the limits creating the configuration of the magnetic field.
The idea of magnetic retention of plasma was suggested by future Nobel Prize winners Andrei Sakharov and Igor Tamm in 1950. 8 years later, the first experimental thermonuclear installation with a magnetic field trap was built in the Kurchatov Institute under the name tokamak. This word subsequently became an international neologism. Tokamak stands for the toroidal chamber with magnetic coils. It has the shape of a donut, a toroid scientifically speaking, with the coils wound around it to create a magnetic field. This configuration turned out to be perfect for retention of the plasma on the ground.
Behind me is a T10 installation. Frankly speaking, the tokamak itself cannot be properly seen due to the abundance of various wires, light guides, and diagnostic systems required to determine parameters of the plasma and perform modern topical research in the field of the plasma physics. As of the moment of its construction, this tokamak was one of the largest in the world. Currently, this is a medium-sized machine, which, however, remains modern and allows us to move towards the controlled thermonuclear fusion.
regardless of the fact that the T-10 tokamak is a massive structure with a height of almost 2 stories, it can be called a full-scale thermonuclear reactor. This is still an experimental installation, albeit with a relatively complicated principle of operation.
Let's consider the main processes that take place here for the achievement of the thermonuclear reaction. First of all, we need a toroidal magnetic field, which is created by the current passing over these coils in order to hold the plasma in the toroidal shape configuration. We also need additional controlling field to maintain stability of the plasma cord. After that, it is necessary, first of all, to create a vacuum in the installation and then supply the working gas. In our case, it will be the mixture of deuterium and tritium. Well, and the moment of truth is about to happen. We've just observed a replica of the thermonuclear reaction.
But how is the mixture of deuterium and tritium heated to such high temperatures that it turns into ionized plasma? In order to carry out a thermonuclear reaction, it is necessary to heat the fuel mix to 90 million degrees Fahrenheit.
We achieved it through using these unique devices, which are called gyrotrons. They are somewhat similar to a microwave oven in principle of operation, but they heat up plasma in the tokamak. The power of each of these devices is about a megawatt.
The gyrotron was designed and created by Soviet physicists back in the 1960s at the Research Radiophysical Institute in Nizhny Novgorod. After the very first tests of the device, it became clear that it's capable of solving the problem of heating the fuel mixture for thermonuclear fusion very efficiently. As of now, 2/3 of modern thermonuclear installations in the world are using Russian gyrotrons.
Gyrotron is designed for radiation within microwave range. Gyrotron generates electromagnetic waves at a certain frequency, and these electromagnetic waves form a narrowly focused microwave beam, which is a kind of working body for various applications, including plasma, heating in thermonuclear fusion installation. As a matter of fact, gyrotron is a relative of microwave oven, its older brother, so to speak. This is because the working range of gyrotrons is wider and the power is higher, but, in fact, it is the same vacuum microwave generator as magnetron.
In order to develop 1 megawatt, this is the power of the gyrotron. Several thousand magnetrons are required. Such a high level of performance is ensured by a whole complex of high-tech solutions. For example, in order to emit such a powerful stream of electromagnetic radiation from the gyrotron, the most expensive part of it was designed, the diamond window.
The diamond as a material withstands high temperatures and has a high temperature transmission ratio. That is, one point is heated and the temperature is immediately transmitted to the periphery where the water cooling is used. The diamond withstands the temperature without melting and cracking. This is why it is the only material applicable for use in powerful devices.
The assembly of 1 gyrotron window takes about a month of hard work. This is without considering the 2 months during which the diamond window is actually grown. It's no surprise that the creation of 1 gyrotron takes 1,500 hours of continuous work. Such a long production cycle is explained by the fact that every device is designed individually and absolutely all parts of it are manufactured manually.
Well, the test and training of a gyrotron often take most time. It can take at least several months. Well, and the whole production cycle takes at least half a year.
It's amazing how much effort and time was put into making this possible.
3, 2, 1, go!
Just like that, simply by pressing a button, scientists from the Kurchatov Institute just launched a thermonuclear reaction. This is an amazing event, but there is no noise, no buzz, no strange smell, or even vibration. It seems that nothing actually happened. But in fact, a real star has just lit up in the depth of the magnetic trap. Ideally, the hydrogen plasma shall be pink. However, depending on which gas is added during the experiments, it can be painted blue, green, or red. The darker the color, the hotter the plasma. However, the main indicator of a successful launch is its uniform glow. Any flashes or sparks indicate the occurrence of a real emergency. For example, there may be foreign particles in the tokamak chamber. However, regardless of the color of plasma, scientists only managed to confine the energy of thermonuclear fusion on a Titan plant for just a second, and this time is not as short as it seems.
It is extremely difficult to achieve these conditions. This is due to the fact that the energy lifetime of the plasma confinement is not very long, and its behavior is very complex and depends on the parameters of the plasma. For many years, we have been trying to achieve the so-called T, which is about 1 second. Little by little, we have come to it.
Tau is one of the variables of the so-called Lawson criteria. It denotes the plasma confinement time in the installation. Another important variable, N, is the density of high-temperature plasma. The Lawson criterion is met only if N multiplied by tau exceeds this value. In its turn, this will mean that the thermonuclear fusion reaction will finally become a source of energy, not just a demonstrative flash of plasma. As of now, the Lawson criterion cannot be met on various installations across the world. With all the success of calculation, an effective thermonuclear reaction is rather a lab success than regularity.
We managed to achieve a nice density, around a unit by 10 to the 14th, but the confinement time of such plasma is extremely low. In other installations, it is possible to confine plasma for quite a long time, but its density is fairly small. On some installations, it's possible to achieve both T and N, but the necessary temperature of the plasma, which is about 10 kiloelectrovolts, cannot be achieved. Therefore, our current task is to combine these three indicators, these components, and meet the Lawson criterion properly.
However, there are certain achievements. For example, the world record in plasma confinement was registered in February 2016 in the Chinese tokamak East. At a temperature of around 90 million degrees Fahrenheit, the scientists managed to maintain the thermonuclear synthesis energy for 102 seconds.
Indeed, the record parameters are currently quite high. But if we express them, for example, in terms of how long a train or a plane could work on this energy, we can see that these values are not that great.
It's been 65 years since thermonuclear fusion was first performed on Earth. However, the attempts to tame the thermonuclear process and make it fully controllable are still unsuccessful. One of the reasons why scientists keep failing is the plasma itself.
Plasma doesn't behave like a liquid, a solid substance, or a gas. Its behavior is completely different. Plasma is something that is characterized by extremely complex laws, and this something is incredibly difficult to control or confine.
New unpredictable processes keep happening in the heated mix of deuterium and tritium, which alter the course of the reaction and raise new questions for scientists.
This seems very easy. This is because all the isotopes of hydrogen contained there are all in the gaseous state. They are all ionized, and the electrons are detached from the nuclei. but their amount is so great that fluctuations lead to formations of currents, and the currents lead to formation of fields. All this, through inverse connections, leads to a very complex behavior of the substance. As of now, we don't have an actual proper theory that would help us determine the exact behavior of plasma inside such an installation.
Experimental research is the only way to study the behavior of the plasma. This is the reason why scientists have been lighting discharges with thermonuclear plasma for over 40 years in the T10 installation, sometimes 30 times per day. Understanding the laws by which it can survive on Earth is a fundamental task.